So, okay, excellent. So let's start. So I'm going to be speaking today. Greg, Greg went to say that I need no introduction. I think I deserve no introduction. So I'll just start. So, I mean, really what I mostly want to be talking to today is the second part and tell you, I mean, this is really for me a big therapy session. Tell you about an existential crisis I'm having, which has to do both with the fundamentals of machine learning and the whole essence of why this whole enterprise, and also related to that, although a bit different, in terms of probabilities and distributions, which are my main, and I think for many of us, our main working tool. And really, I take them for granted. And I remember there was maybe Greg also remembered this. There was when we were grad students, there was some discussion in the AI lab at MIT. And you do remember this. And there's at the time younger people that are now retiring, and there we're using statistical approaches, and then there's the good old-fashioned AI. And Randy Davis, who is definitely a very good old-fashioned AI, but he said that. Okay. He accused, I think he put it out at some point. I think it was John Fisher or something. Greg doesn't want you to mention names, that he's a probability fascist. He actually used a different, stronger word, but it was to you. Okay, accused Greg of being a probability fascist.
That's because they had the wrong formula for the base rule.
Okay, so the thing is that but really, what I'll talk today is a bit about how really maybe rethinking whether really thinking of things in terms of distributions is the right thing. So the first part will be a bit more constructive, a bit lighter, and talk about one way in which we're successfully shifting away from talking about distributions. But I really hope to have time to talk about the second part, which is a bit harder for me. Okay, so let's start with the first part. And much of what I've been interested lately, and I think it's hard not to be interested, is large language models and huge success. And basic question is, what are even these large language models? What should we think about them? What tasks do they actually solve? What do they? And how should we be evaluating them? So one simplistic answer, if you ask, okay, what is a language model? You ask Shannon, what is a language model? Okay, a language model is just a distribution over strings. Okay, distribution over text. We specified maybe using a next token predictor, so some functions and maps the text so far to a distribution over the next character. But this is just a way. This induces a distribution over the entire text, and really the object is just a distribution over texts. Okay, so with this view, we can just think of large language models as density estimation. The goal is density estimation. There's this distribution over text, distribution over language, and we want to approximate it. Okay, but now we should ask several questions. Well, first of all, in what sense do we mean that we approximate it? What's their function? I can talk about that also for a full hour. I'm not going to talk about now. But also, why do we actually want to do this? Why do we care about what's the utility? What's the value of approximating this distribution over text or language? But maybe even another question, what is this distribution even that we want to approximate? What is this distribution over texts? Okay? And I would argue that there's no such thing as distribution over text. It's kind of like a meaningless thing. Okay? So for one thing, if you talk about all the texts in English, right? There are many different types of English, right? There's newspaper articles and scientific papers and emails you write to your friends and posts on Reddit. And even if you maybe could argue, and I don't think you can, that there's some distribution over the text and posts on Reddit, what is, to talk about distribution over language, you also have to tell me what percent of language is Reddit and what percent of language is Wikipedia and what percent of language is Shakespeare. And I don't think this is there's any way to make this meaningful. And different sources have very different weights. In particular, yeah.
I'm a bit confused. Why can't we? You just said that there's some percentage who might not know this, but you can model it.
I don't think it's a matter of knowing this. Well, you can model it, but you can decide that 32% is Reddit and 17% is Wikipedia. But I don't think that represents anything real. I don't think there's any meaningful way to say that 17% of the text in the world of the words ever uttered, or in that case, most language is Chinese, right? It's not I don't think this is
And we can model that.
Yeah, but I don't think it's useful. I don't think it's meaningful. Okay, so then yes, Sasha.
How about a collection of distributions?
So you can talk about collections of distributions, but again, I think that I think that even within one, and let me go on. This is just the first point. This is not really very meaningful. And moreover, I think that even if you do think that there's some distribution, it's definitely non-stationary. I mean, it changes over time. But not only is it not stationary, it's also interactive and reactive. I mean, the language actually changes as a response to language. In a month of now, changes in response to the language now, and moreover, changes if we have some system that is based on modeling language in some way, that itself is going to influence language. And so what we care about really is not random text. In some sense, what I care about is whatever text you interact with the system, and the system itself is going to affect that. And actually, I think even easier to think about not in the context of language, but actually maybe appealing to Greg in terms of images. I don't know what it means to have a distribution over images either. I think it's completely meaningless. It's just like a random picture shot, taken in a uniformly random place in the earth in a uniformly random direction. It's just like basically just going to be a blue image with nothing on it, right? And I think one example of this reactiveness is an application like iNaturalist. Probably some of you are familiar with it. You take a picture of a flower or of a bug or of whatever and identifies it. Okay. So you can train it based on pictures that people took in Flickr of bugs and flowers and so forth, and that represents some maybe defined distribution. But now when the app actually works and people use it, then they're going to take different images, and what images they're going to take are going to depend on how does this app work and how well does it work. Okay? And so I don't think there's any meaning here to talk about the distribution over images. Okay? And I think that the text and AI systems we have now, in a similar way, I mean, the way you interact them, the type of things you feed to them and you want them to do depends on actually what they do. Okay, so but more than that, it's also not clear to me what's the utility, I said, of modeling this distribution that doesn't exist anyway. So I think a better view, is to think of what we're learning is not actually a distribution, but a generator, something that generates language. Okay, and so based on examples, so now it's not exactly density estimation bound. We have examples of texts, correct, good, whatever texts in the language, and you want to generate new texts. Okay, so now if your task is only to generate new texts, to generate good texts in the language, that's extremely easy. Okay, how would you do that? How do you generate a valid text in the language based on
just output one of the
just output one of the input text, right? I mean, that's great. Also, you want a face generation system. You feed it like a million faces. You don't need to train it. Just output a random face. I mean, that's going to be a completely valid face. Okay. If somebody can figure out how to turn on the light, that'd be great. Okay. Or maybe ask Alicia to. Oh, you got it. Thanks. Okay. But the thing is that this is kind of like. Okay, I don't know if this is useless. I think this is kind of useful, but at the very least, it's too easy. So it's not like a good task to think about because then it wouldn't be challenging enough. And so you can ask, okay, I want something that's good, but it's different from everything in my training data. That's new. Okay. So indeed, there's been some attempts to think about language models in this way. I think most influential is the work by Kleinberg and Mulyathan that basically said that okay, this is about generating new things that to be both new and good. Okay. But actually, I'm going to soon try to rebut this because I actually am not sure why things need to be new. Why is it important? Yes, Karen?
You can also talk about discriminating between sequences that are in the language versus
that's
sequences
true.
that are
You
not
could.
in the language, which is more well-defined and meaningful.
That's correct, but that's absolutely correct. That's a very well-defined task. However, that's not what it's different neither how we use large language models, nor are they actually particularly good at that. Okay? And they're not necessarily, this is definitely not how we use them, and so this is, but that would be another approach, but not the one I'm taking here, and I would argue not the one that I would find satisfying. But okay. So I would argue that this newness is not really important. I don't actually care about being new. What I care about is just being good, and I'll try to convince you this in a second. But the key to me is that what you want to generate is just like a random face or like some random text. It's very easy. If you just want a random text and just open, get some random stuff from the internet. What we want is actually a response to some prompt. So this is very important that we want something that answers our question. So our view, at least in the first half of this talk, actually throughout the talk, is the way we're really thinking of these large language models is this question answering systems. We have a question X, and they give us an answer Y, or maybe a distribution over Y. And again, if we have once we have this distribution, it's well defined. We just look at the conditional, the marginal distribution of an answer y conditional on the question x. Okay, and now what do we want from it? So we want the answer to be good, and we'll capture it through some reward function or utility function that measures how good is the answer to this question. And what we want is to maximize this value, expected value, the expectation of the reward they get by answering questions in my system. Okay, so let me try to convince you now that what I want is really just to maximize utility. I don't care about distributions, and I don't care about newness. And let's look at answering some questions. Okay, so let's look at what would be, how would you want to evaluate the system? Yes?
There was a distribution.
You caught me. I was going to get to that only in 20 minutes. So get back to that in 20 minutes. That's going to be an important point later. Okay. Okay, so let's look at, first of all, the most common question on Google. The most, the OpenAI and Anthropic doesn't release this, but Google actually can tell us what is the question that asks Google the most. Any guesses? Any knows this?
What's the weather?
How many ounces in a cup? Okay. Okay. What is the answer here? Come on. 8. Okay. 8 is correct. Okay. It is not new in any way. Okay. This question has been answered many times. There's nothing novel about it. Nothing needs to be novel about it. Nothing needs to be new about it. It just needs to be answered 8. There are several correct answers. The answer could be the digit 8, spelled out 8, could be the sentence, there are 8 ounces in a cup. There are a bunch of different valid ways to say this, but it's not like every time you get asked this question, I have to answer it in a different way. I can always answer it the same way, 8. Okay? Let's look at some questions that are maybe a bit more complex. So another thing we ask language models to do a lot is to rewrite something, or rewrite this paragraph, I don't know, with all kinds of stuff. Okay. Also here, if I want to rewrite a paragraph, ultimately the way I want to evaluate it is I want to evaluate it that it actually matches my criteria, is good. Okay. It's not, I would argue that here people say, oh, but it's important to have diversity, to write it differently in a different way, to have new. I would argue, no. If you really want this to be different, for example, from some other stuff, then tell it in the prompt, and that'll be part of the utility that rewrite this paragraph in a way that's different from my last 7 papers, okay, or that's way they're different from some other thing. Okay, but I don't think that inherently newness is important here. Okay? Another example. Again, I don't need to match some distribution. Another example where I really don't want to match a distribution. Okay, this question: what is a prime number? Okay, so if you wanted to match a distribution here, okay, of the people, I don't know, random people on Earth or something like that, random people in the U.S. I don't know what your distribution is. Whatever distribution you're going to match, it's going to be really bad, right? Most people will not actually be able to give you a correct, let alone succinct definition of a prime number. Okay, what I want is to actually not match the distribution. I just want to have a correct answer, a correct and useful answer. Okay. Another place where people maybe say, oh, it's important to match distribution. Let's look at this question. Okay. Okay. What's the answer here? Okay. So some people would say, well, we should match the distribution. If 56% of the people think one way and 44 think the other way, then we should give answers that match that. No, that's nonsense. I don't want my system every time to give some controversial question, some different answer. The correct and the answer that has the good reward is this is a controversial question. 56% of people think one way, or 56% of adults in America think one way, or whatever. There are 2 possible ways to view this. Okay, I do not want to match a distribution. Okay. Yeah.
So just, I don't know if we will get any reproductive of this, but I think in most of these things, with the possible exception of the second, the fact that the output of the model's language is masquerading, it's something masquerading in language, but you're really asking it for something else, right?
Maybe not something else. I'm using it. Okay,
well,
wait. I'm representing. I'm using language to represent it.
The answer to the first one is a number.
My language is a medium representation. So I should have also talked about it before. And then I talk about distribution for language. A lot of what these models output is not just programming languages, but also XML and all kinds of other stuff. Right? It's text really. It's not language.
I understand.
Okay. So the way to think about it is text, not language. And the answer to all these are text questions with text answers.
I understand. But for example, if you're asking a person, should abortion be legal? The person tells this controversial question 56%. that would be a very strange response because that's what usually what you mean when you ask someone this question. What is their opinion?
But when I ask,
now we couldn't care less what's our opinion.
Okay. Let's argue about it later. But I'm not asking a person. I'm describing. I want to build a system, and how do I think my system should behave? I think that if people are going to pay money to use my system, it should not give them an answer, a random answers that matches distribution, and give them a useful, instructive answer. Okay, so it's meaningless to say what is the opinion of the system.
All I wanted to record kind of as a note.
Record it, it's okay.
Yeah, is that language was, emerged as a
You keep saying language, I'm saying text.
But, okay, I'm going to talk about, well, you're talking about language and not text.
Okay, I'll continue talking about text from now on.
But language emerged as communication between people, and it carries various things about that. And some of the things, it makes no sense asking LLM this question. Like,
I think all these questions match complete sense. These are exactly the questions people ask LLMs. All these questions are people ask LLMs. Okay, let's go to another question that you also, Greg, would object to. Maybe this is another version of the other. It's not so interesting, but again, you can ask a similar. Who is the best football player ever?
Pelé.
Exactly, I think so too. But some people here might have all kinds of strange other answers. Okay, so here also, first of all, everyone thinks Pelé. I actually am not sure between Pelé and Maradona. Okay, I don't know. There's
most people have thinking about what that has to do with football.
Exactly. In fact, okay, maybe the correct answer here should mean, do you mean soccer or do you mean American football? Okay, I mean, that would maybe also be here a very high utility response. Okay. More to the things I really want to do is, for example, let's get this, prove the square root of 2 is irrational. Again, we're not talking about distribution because most people can do that, but I am assuming that all people in this room can actually write a valid proof that the square root of 2 is irrational, okay? And I'll get a whole bunch of different proofs. Each one of you will write a different proof. Actually, they're not going to be all that different because there's not that many ways to prove it, but if you write a LaTeX file for it, all your LaTeX files, I don't know, there are like 20, 30 people here, I'm going to get 30 completely different LaTeX files. There's absolutely zero chance that two of you will write the exact same LaTeX file, which is an answer to this question. All of these are completely valid answers, and I don't think it's meaningful to talk about, again, a distribution over them. Maybe there's a distribution for them over people in this room or whatever. I don't care to model it. Again, I just want to get a good answer that's correct. Anybody know what this question is? This is really wonderful. So this is the only answer from the last Math Olympiad that none of the language models actually got correct. Okay. So again, all I want is to get the models to actually be able to get an answer to this question. Okay, you can think about this later if you haven't seen it before. Okay, so let's just summarize our prompt response view. We think of our language modeler as a policy, as giving a distribution of answers given a question, and we have some utility function. Our goal is just to maximize that utility. Okay, so how are you going to do that? So first of all, to tell you what the learning setup. So at least what we're going to consider here is we're going to learn from demonstration. So what I'm going to go is I'm going to go to all you smart people, and I'm going to collect a bunch of answers to questions. So I'm going to draw questions from my distribution that very correctly I do need to have a distribution over questions. We'll get that later. And then for each question, I'm going to go to one of you and get an answer. Okay, and so I have a data of questions and answers. Okay, and let's assume that all your answers are correct. I mean, or maybe at least very good. And what I will do is the system that answers as good as all you guys, which again just means that if you're 97% correct, the system also is close to being 97% correct. So how can we do that? Okay, so first of all, we have to learning. You have to have some inductive bias, some assumptions. Okay, one approach to take is to say, let's model how you answer questions. Okay, so what we're modeling is you. I'm viewing you all as generators. Okay, and I have a distribution, a model for the class of possible generators. Now note that since I collected answers from all of you, it's not going to be any one of you particular. My model is from the process of going to a random person and then getting an answer for them. Okay, and if I have that, then what I can do is now I have probabilistic class of probabilistic models. So this is kind of the Greg approach. This is very probabilistic, very distributional. You're sitting in front center, and you expect to get picked up. Okay, and then and the kind of right thing to do here is maximum likelihood estimation. Okay, we can do maximum likelihood estimation in this class. So it's actually here maximum conditional likelihood estimation. Estimate and match the distribution of find the generator in our class that best matches the observations. And what you can show is this in fact works and works with sample complexity that's exactly what we want. It's proportional to the low cardinality of our model class. And what we get is a guarantee, it's actually a very strong guarantee, that I'll actually find an answer that answers with the same distribution that I have in my training data. Okay, so that's great. In particular, if I answer with the same distribution, then my value is also as good. Like I'm basically, what I'm doing is I'm essentially cloning you. Okay, so this led, this is in this paper is behavior cloning all you need. It argues that really the way to do things to get high value is to clone the training data, to clone the distribution in the training data. I just want to, as a side note, there's this low cardinality here. I mean, this low cardinality. What is the low cardinality? I mean, it's really the complexity of this model class, and the way to think about it is really the number of parameters, right? So if you have, some system, it doesn't matter what it is, a transformer with whatever, I don't know, and it has some number of parameters, it's 1 million parameters, its low cardinality is roughly 1 million. Okay, more exactly, it's 1 million times, I don't know, the number of bits in the parameter, 32 bits, maybe even less these days. Okay, so really whenever you see low cardinality, you should think of it as number of parameters, and whenever you want to think about number of parameters, you think of that way. And also, and of course, we're talking about the number of parameters in this generator class, but that's the same as the number of parameters in your next token predictor. Just using the next token predictor. Okay, I think this answer is most satisfying. This very crude view of just thinking of low cardinality as number of parameters is most satisfying for most things. But if really you think that actually parameters are not 32-bit floating point numbers, but actually real numbers, because you maybe think real numbers exist. Does anybody here think real numbers exist? We already had this discussion last year. Okay, Julian thinks real number exists. And indeed, Julian, because he thinks real number exists, was worried about this and said, okay, but what about if the parameters are actually real numbers? So that's fine. We can also replace it by the VC dimension of the generator class, which for transformers, Julian and Chinshao, together in the Jinzhao and Chinshao, they showed that it is indeed also bounded amount of parameters, maybe up to some log factor. So you're fine even if you think real numbers exist. But anyway, this is not the point of today's discussion. The question I want to ask is, do I really need this behavior cloning? Do I need to clone at all? Okay. So in particular, the answer here was based on matching these distributions. Do we want to match the distribution? So I'd argue that instead of having this assumption about the generator class, what I want to go to is a much, much weaker assumption, something at least I'd argue is a much weaker assumption. And in particular, just assumption on what does it mean to be correct or not. So instead of having a class of generators, just think of that your inductive bias is on the possible notions of correctness. Okay, so there's some true notion of correctness, and you don't know what it is, you just know it's in some class. For example, again, measures of correctness induced by some transformer class. Okay? And importantly, you don't have any assumption here or how your demonstrations are actually generated. Now, if your demonstrators are optimal, you actually do have an assumption, right? Because you know that the demonstrators are generated in a way that's optimal with respect to some notion of correctness. Okay? But what I'd argue is that starting from the reward class is a much, much weaker assumption in the following way. That it's true that if you assume your rewards, the correct rewards in some bounded capacity class R, then the policy class is in the corresponding class of all the optimal ways of answering those questions, but that class can be much, much, much larger. And the main reason, as we said before, there are many, many different ways of answering questions correctly. Literally exponentially different ways. And when I say exponentially, I actually mean it in its mathematical meaning, right? Because think of, again, you're proving that square root of 2 is irrational, you're writing a LaTeX file, and there's some entropy in every character in that LaTeX file, right? You can write your sentences in different ways, use different small words in between, use different letters, and so you have some entropy rate that scales, some entropy rate, and so your entropy scales linearly with the length of the file, and so the number of possible correct answers is exponential in the length of the file. There's really infinitely many essentially correct answers. And the generator can choose any distribution over them, and it can choose a different one for each question. Okay, and so the number of possible policies, optimal policies, is much, much, much larger than the number of possible rewards. Okay, the other way though, it doesn't work. So if you fix to a particular, if you fix a policy class, you can think about a reward class that kind of implies it. That's only as big as that policy class. So in this sense, the reward class assumption is much, much, much weaker. If I have a reward class assumption, I have a notion of some inductive bias and a notion of what does it mean to be correct. And Greg thinks of inductive bias in terms of how do people answers, my inductive bias would be much better. It would be a much, much smaller number of parameters, much less low cardinality, and should be much better for learning. Yes?
Just maybe a constructive example. Suppose we're asking for a proof, and correctness is defined by the foundations of mathematics.
And here I'm thinking of learning what are the foundations of mathematics. So this is
It's exactly what I'm suggesting.
Okay.
Right? So the inductive bias would then be how many correct foundations of mathematics are there?
which
It's
are
much
very
smaller.
much smaller.
Much smaller.
Exactly. Okay, good. So now, what can we do with this assumption? Just inductive bias, just in the notion of correctness, not in the generators. Okay, so what I can tell you first of all is what doesn't work. So maximum likelihood estimation doesn't work. Okay, we can show it fails. I can ask Nirmit if I'm not going to work. I mean, I'm starting to run out of time, so I'm not going to work off this example. But maximum likelihood estimation here fails. And in fact, it's not really maximum likelihood estimation's fault because maximum likelihood estimation inherently tries to match the distribution, and cloning is just not possible here. Okay, you cannot, based on just an assumption of the reward class, you cannot hope to clone the demonstrator. Just information theoretically, you don't have enough to go on. Okay, so all approaches based on cloning are doomed. Okay, so does that mean we're doomed? Okay. Well, another thing we can try to do is to try to directly learn the reward class, directly learn the foundations of mathematics. Okay, bad news, David. That's also impossible. Okay, so this again, there's just not enough kind of to go on here, not enough that the problems to underspecify.
God gave it to us.
In particular, because one way to think about it, we only have positive examples about the reward function, not negative examples. So this is also not possible. So are we completely doomed? Well, it turns out it's not. We're not. What we can do, even though we cannot actually clone the demonstrator and we cannot learn the reward function, what we can do is we can still learn to answer as good as the demonstrator. Okay, importantly, we're not going to answer the same way the demonstrator answers, but we're going to answer as good as the demonstrator. Okay. Okay. So let's try to see how to do that. So is the setup clear here? The question clear? Okay. So. In order to do that, it'll be easier for us to go to an online model. Okay, this is basically the same thing, but now think of it as we're playing kind of in rounds. In each round, okay, Greg is getting annoyed that I'm picking on him. I'll come back to you soon, so don't worry. At each round, I ask David a question. Okay, and David is my learner. Okay, so David gives me an answer. Okay. And the answer is either correct or incorrect. Let's just think of correct or incorrect now. We can extend everything real value rewards. But I don't tell David if it's correct or incorrect. I just have a little notebook that I'm marking him wrong or right. But he doesn't see his mark. Okay. And then I actually give to David the correct answer, demonstrate to him, show him a correct answer, y tilde. Okay. So David, he knows the answer I gave him is correct, but has no idea if the answer that he gave is correct or not. Okay. And we can, but he can use my demonstrated answer to update his system. Okay. And then at the end, I score him and see how well he does. Okay, and it's very important here that David, as we go, he has no idea how well he's doing. He has no idea if his answers are correct or not. Okay, okay. So how can we do it? So a baseline approach here, what David could do, it's very natural, is every time he sees an answer, he can kind of say, okay, all these notions of correctness that are not consistent with the demonstrated answer are definitely not valid notions of correctness. Okay, these are those I can throw away. Okay, so he's going to do that. He's going to represent that with a weight. It's going to start. All the weights are going to start to 1. He's going to just zero out the weight of anything that's impossible because it's not consistent with demonstrations. And then a sensible thing for him to do at each step is just take all the possible models that are left and basically answer based on their pick an answer that satisfies the largest number of them. Okay. So answer based on this satisfying the largest number that are still okay. So this is a valid approach, but unfortunately, the number of mistakes we can guarantee to make here is not log cardinality, but actually scales as cardinality. Okay, and this is really bad news. So now instead of talking about learning with a sample complexity which is log number of parameters, which is number of parameters, we have a sample complexity which is exponential in number of parameters. Okay, that's like a complete non-starter, and that's not a good approach. Fortunately, we can very easily fix it, and to fix it, we have to do the following, just one strange trick would fix all your problems or something like that. Forget all these bylines, okay? All David needs is one strange trick. So what is this strange trick? The strange trick is every step, David actually generates an answer. He doesn't know whether this answer is correct or not, okay? Maybe it is, maybe it's not. But he's actually going to basically assume he's always wrong in a soft way. And what he's going to do is all the answers that are all the models that are don't agree with the answer, all his answers that said that all the models that said his answer is wrong, he's going to upweight them. Okay, so it's kind of like it's strange, right? He's kind of like guessing an answer and then saying, oh, but actually maybe it's wrong. Let's like upweight everything that said that it's wrong. Okay. Okay. And the thing is that that's enough. That little change is enough now to reduce the number of mistakes and hence also the sample complexity to just the low cardinality. Okay? And okay, I really want to get to the second part. I'm going to go through the proof here. I want to just flash the proof real quickly just to show you how simple it is. Even though the speed I'm passing it, you might not get it, but really it's literally 2 lines. So all you have to do here is 2 things. Okay? One is we have to keep track of the total weight in the system. And what we first thing to argue is the total weight, like the sum of the weights of all the predictors, is monotonically decreasing. Okay? So the thing is that, of course, when we zero things out, it's decreasing. What happens when you double it? And the point is that we double it. We double the stuff, since David is going to choose the answer that answers the most things correct, the things he doubles over here, okay, is necessarily less. The correct answer is less popular than his answer because his answer is the most popular. And so the stuff that he doubles is less than the stuff we remove. Okay, so we can think about it a bit later. So that ensures that the overall sum of the weight is decreasing, or at least not increasing. But every time David makes a mistake, he doesn't know it. But every time he makes a mistake, he's going to double the weight of the actual correct model. Okay, that's what it means to make a mistake. That means the correct model is one of those that actually didn't agree with this answer. Okay, and so the total weight is at most the cardinality. The number of times he can double that is the most low cardinality, and we're done. Okay, that's a really simple proof. You have to work a bit harder to extend it to real value losses and to being only approximately correct, like if you're only 97% correct, not 100% correct. I'm not going to go through all the details here, but just say that bottom line, and after learning to batch conversion, you can get this only in a statistical setting, and say that if you have data from some policy pi tilde, that again, I don't make any assumptions other than the fact that it has good value, you can learn a policy pi hat that has value almost as good as pi tilde. Again, it might be very different than pi tilde, but the value is going to be almost as good with sample complexity that scales linearly with the number of parameters in your reward model. And you also get here this optimistic rate that I really like. So delta you should think of as the suboptimality of your policy, how far you are from 100%. If you're really optimal, if you are always correct, I only have this 1 over m term. I don't have this like square root of term, and then kind of I scale gracefully if my demonstrator is only a bit inclined. Okay, interesting story here. So this is, I should have said at the beginning, I'm going to say it soon again. This is work led by Nirmit together with also Jean and other collaborators in Amazon and Kong. And after we did this, we thought this was really clever. I was really, really happy with this. I mean, Nirmit had some really excellent ideas here. And then I was chatting with somebody, with Ishai Mansour actually, and he said, "Oh, isn't this like what Rob Shapiri did in 2007?" Okay, yeah, it is what Rob Shapiri did in 2007. The exact way they view it is a bit different. I should say it's much more complicated. Our approach is much simpler, kind of one pass, also much simpler. The proof is much simpler. Everything is much simpler, so we can also generalize it more easily. It also gets you a better rate. So I think this is still very nice. I'm kind of happy that Nirmit wasn't aware of this work by Rob Shapiri. And sometimes reinventing the wheel is not a bad idea. But we did kind of reinvent the wheel here. Okay, so yeah. Schmidhuber, I'm sure, did it already 10 years earlier. But Rob Shapiri actually really, this is, they really, again, it's not one-to-one the same thing, but, okay. So again, this is what I described to you now, is work led by Nirmit with Jean Sidroth, who some people might remember from here, is now in Amazon, in Shiva from Amazon, and Kong from the Stats Department. Okay, so what we did here, we started departing from distributions, and the main advantage we're getting here is that we're not trying to model the distribution of the answers. We're just trying to get them correct. And that allows us to break away from this cloning and do things that are not possible if you insist on modeling distribution, if you insist on maximum likelihood estimation. Okay? But as was pointed out here, I still have a distribution. I didn't really get away from this distribution that I don't believe exists. because I'm evaluating here based on this distribution of questions. Okay, so it's not a distribution over of text, it's a distribution over questions. But there's also no distribution over questions, just like there's no distribution over text. It's meaningless to talk about a distribution over questions. For example, David, what percentage of math problems can you answer correctly? That would be your value, right?
Which book?
This is a completely meaningless. Oren is here, my son. They can ask maybe Oren this question. Sorry to put English. What percentage of math questions can you answer? What? No? No. Oren, maybe actually, when I asked him, not Oren, but actually some other kids, they have an answer, okay? They can say, oh, yeah, I can answer 87% of questions, right? Because they got an exam, and they answered 87% of the questions. But what is this distribution over questions? It's completely meaningless, right? The way we want to think about how well you answer questions, there's no distribution of questions in math. In fact, if anything, we want to evaluate things, the more reasonable way to evaluate is not Oren can answer about 87% of questions, and so can you, because the questions you're working on are ones that are probably you can answer about 80% of. Everybody can at any given moment answer about 80% of questions. Okay, the real way in which maybe some of you, Oren, sorry to put the way, or maybe some of you are better at math than Oren, is not because you can answer a higher percentage of questions, but you can answer more difficult questions. Okay. So one thing we're working on, this is started with work with Matt, not here in Again Kong, and the stat student Yipeng Yang, and now wrapping up together with Ben Recht, is really thinking of evaluation not in terms of saying, okay, this predictor is good because it can answer 87% of questions, but this predictor is good because it can answer hard questions, and evaluating things in terms of hardness and inspired by item response theory. But this I'm not going to talk about today. I hope maybe next year. But the core issue that's really more bothering me here is this notion that we're still here, even in here, we're going to have distributions hidden somewhere. We're just going to have some latent hardness maybe. Okay? But really, I really want to talk about things without a notion of distribution over questions, over text, because really what we want to do, I want to learn to reason. Okay? And once you reason correctly, okay, you're correct. Even outside your distribution. This is what we want to do. We want to be able to, we learn to do math and all kinds of textbooks with random questions, but then we take this knowledge that we have and apply it to really out of distribution things. And if we learn to reason, we should be able to do that, okay? And how can we do that? Okay, so in order to, and now we're getting closer to my existential crisis, and the person most responsible for my existential crisis is Chen Shao. He's been causing me a lot of grief in recent months. And in order to describe to you my existential crisis, I'll first talk to you about some work led by Chen Shao, together also with Jiwan and David. That's okay. The next 2 minutes is still, there's no crisis. It's very good, and all is very good, on reducing context length in large language models. So, as you know, the way we use these language models instead as generators, it's not really distribution over anything. It's really as reasoning agents. Okay, and in particular, the way they can really solve complicated problems. And this problem, okay, this is I took from my talk last year. It's not so complicated, but still, even to answer this relatively simple problem, the way they solve it is they go through many, many reasoning steps. So each kind of generation is just a reasoning step. And then by doing that, by thinking a lot, they can kind of arrive at the last answer. And then this is really going in complete steroids now, right? I mean, you ask something from OpenAI, from a GPT, and it sometimes thinks for 40 minutes before it gives you an answer. I have no idea how they're funding all this compute. I mean, I think they're losing money on it. But it's really, there's a lot of this generation going on. And the thing is that when it's thinking, also the context, what's going on into the LM keeps getting longer and longer and longer, because you add, every thinking step, every computational step, every reasoning step, you add to it. And so the context length scales as the length of the computation, the runtime for solving the problem. Okay? So if you want to solve really hard problems, really complex problems, you have to run for a long time. That's unavoidable, but then you get into this very long context length, and then your model goes boom. Okay? Because our models right now have a really hard problem handling these large context lengths. Okay? Okay. The thing is, the main problem here is that it's really the only way it knows how to think is to continue adding things to this context. But you guys can do much better than that. Okay, so if I took you, any one of you, and gave you a small whiteboard like this person has here, and I asked you to solve a very complex problem, okay, you'd still be able to do it, even if you have to. I mean, I have to at least write every time I think. Students know this. I have to write everything, but have somebody write at least on the board. Even if you have to do this, you can still use a small board, because the way you do this is you'll use the board. You'll maybe solve some subproblem on the board, but after you solve the sum problem, then you have this tool. What is this? This is not a cell phone, apparently. I mean, this is generated by Gemini, so it looks like a cell phone. It's an eraser, okay? And what you'll do is you can erase the kind of derivations leading to the solution of that subproblem or the proof of the lemma or whatever, and now you can only save the final answer. Keep going, okay? And so the idea is that you want to be able to erase and work with context length that's only as long as how much memory you need, like how much you have to save. You can remove all the intermediate calculations. Another way to think about it is through functional or modular programming. Each time you call a function, it does whatever it wants, but when it returns, it can remove all its internal storage. And this both has an advantage of saving storage, and what we really want to hope also is it's also more natural, right? This kind of modular way of solving problems more mirrors how we maybe should be solving problems. Okay? So indeed, we have two ways of doing this. One way, which is actually the second way you came up with, but the first to get out is called pencil, and it's a very, very, very simple modification to the standard autoregressive process. The idea is we had one simple trick. Everything is just one simple trick. We had a rewrite rule to our generation. And every time we have three special tokens: call, separate, and return. And every time we have like a sequence of something and then call and something and separate and something return, we remove the something in between. Okay, let's see how that works. So basically, each time you generate a new token, right? So you feed your current context into the language model and get a new token. If this new token is not a return, just keep going. But if this token is a return, you look for the previous step and the previous call, okay? And you refer to all this as this is think of C at the context you had before. This is the thinking that was inside the call, and this is what needs to be returned, the answer, okay? And so you remove the thinking and keep only the answer. And that's the only, now you just apply this every time. That's very, very simplification. You don't have to change the transform or anything, okay? And that allows you to basically encapsulate all this thinking. Yes?
It requires you to know that you're about to embark on something you're going to erase at the time.
That's true. So that's called calling a function, right? I mean, you also do that, right? When you think through something and say, oh, let's solve this subproblem first. That's a good thing. You should be doing that consciously, I would argue. And definitely when you program, you do that, right? I mean, the computer does that, right? You call a subroutine. So you know you're going to starting a process that when it's going to return, it's going to release its local storage. Okay? In fact, the other approach, which is recursive language models, does that even more explicitly. It's a bit harder to describe with one line, but in some sense it's more natural, and it does exactly what I just explained to Colleen. What it does is now there's additional call and return. So now there's 4 additional tokens: a call, an end call, return, an end call. But roughly speaking, what happens is, again, we give the language model an opportunity to call another instance of itself. Okay, so now it's basically explicitly start a subcomputation answering this thing. Now we start a new instance with a new context, separate context that that does that computation. It can in turn call recursively additional copies of itself, and when it's done, it brings the answer back up. Okay, so you don't have to, but this is kind of local to the calling to the called model. Okay. So both of these methods, what they definitely allow you is significantly reduce the context length. This is particularly important. The way we demonstrate these problems requiring a lot of runtime, but maybe not a lot of memory, like all these like search problems over like combinatorial search, like constraint satisfaction problems. This is an example of quantified Boolean constraint satisfaction problem that you basically just have to. Don't bother looking too much in the tree. You have to like do some search in the tree. This is the whole chain of thought process written out. You check everything. It's very long. Okay, it's a small problem because I have to make it fit in the slide. But the thing is, if you do recursive calls, what you see here is that the overall context is just as long, but each particular context at each step is maintained as very small. Okay? And you can do this also with, this thing works also with very like natural language type, also constraint satisfaction problem, any type of problem you have to like search a lot but only keep around small things. Okay, so this works, this is great, it reduces the, I'm going to flash some slides here, reduces the context length you need by like a bazillion, by a lot, and so lets you solve much, much bigger problems, and we can successfully solve where is that? I'm sorry, a while since I seen this. Where is this? This is us, this is them, and we can get 100% even though standard COP things start failing when the problems get very big. We can solve much, much bigger problems. Great, okay, so everything is great. And the reason we're solving these problems, I should tell you, it's kind of cheating. Because what we're saving on is just the fact that the context length, we can handle much, much larger context length. So we are actually saving on compute, on runtime compute, and implementing that tension. Okay? The reason we're here beating all these other models is because we're running this with fixed context length, and all these other models are basically running out of context length, and we're in none. So that's a clear gain. Okay? But the question is, are we gaining something a bit more fundamental here? In particular, other than the gain reduction in context length, it seems that this modular approach also better mirrors kind of how to solve problems. It should actually lead us to better learning. It seems like it's a better inductive bias. How much time do I have? 10 minutes. Okay. It seems like a better inductive bias. Like this type of, instead of this long serial thinking without any structure, this modular structure should introduce good inductive bias and should actually aid in learning, in generalization, reduce the sample complexity. Okay? So does it? So unfortunately not. Okay? We really tried. It doesn't empirically. It also doesn't theoretically. Okay? So in what sense does it not theoretically? Okay. So we understand why it doesn't. So the thing is that if Greg is using standard COT, okay, and I'm using this fancy either pencil or recursive models, or maybe Chin Shao is using the fancy recursive models, then the thing is that anything Chin Shao can do with a transformer, Greg can actually also do using standard COT with just a transformer that's a tad bit bigger, really not much. Okay? And so in terms of inductive bias, Chin Shao doesn't actually have any advantage, because the hypothesis class that Chin Shao needs is only maybe like a tiny smaller than the hypothesis class Greg needs, right? Greg's transformer class can just do just the same, and that's why we kind of don't have an advantage. Yeah.
So this refers to the size of the model. What about the size of the context? Is there also, can I also say I can do the same thing, but just as big?
But the sample complexity doesn't depend on the size of the model. It's a good question. The key is the sample complexity doesn't depend on the size of the context, kind of. Julian will soon interrupt me.
There's some computation. There's more computation.
The sample complexity only depends on one thing, which is the low cardinality, which is the number of parameters. The number of parameters is the size of the model. It does not depend. How much you're going to burn your GPUs doesn't matter. So So to be a bit more fair, if you're compute bounded, so if you're going to use standard COT, and Chin Shao is going to use recursive language models or pencil, and you're both going to have 32 GPUs running for a week, Chin Shao will be better than you. And the reason he's going to be better than you is in that week he can process many more examples than you, because processing any examples you're going to have to sweat much more. So that's true, then there's benefit. But if you're going to process the same number of examples, it's going to take you much, much longer, right? But you're going to process the same number of examples, then he doesn't have any benefit over you. Okay? So that's true, and I intentionally kind of want to, but that's, I think is I expect in the beginning to actually have also a benefit in terms of learning, in terms of sample complexity. Okay? And there is no benefit. Okay, so to understand why I'm saying there's no benefit here, maybe it's important to go back, and now we're getting closer to my existential crisis in less than minutes, to what is the whole basis of our endeavor here? 10 minutes. Why does machine learning even work? Okay, in order to understand that, I think the core way to understand it really goes back to think in terms of the standard decomposition to approximation error and estimation error. Right, if we're learning some hypothesis class H and just minimizing the loss in that hypothesis class, we can write the loss of our learned predictor in terms of the approximation error. That's the best we can do with our hypothesis class. Regardless of learning, it's the best possible we can do in the hypothesis class, plus an estimation error that depends on the low cardinality of the hypothesis class. And the important thing here is in order to learn, your hypothesis class doesn't actually need to model the world. It only needs two things. It needs a good approximation error, a good estimation error. So it only needs to approximate reality well. Okay, so the approximation error is small. Okay, so you have to get a good generic approximator. And it needs to be not too big. But not too big, again, because of that log is pretty generous, right? It has to have a small low cardinality. Okay, so you can have very generic approximator. In particular, the right generic approximator to use is just short programs. That's an excellent generic approximator. The low cardinality is pretty small, just as long as a program, and you can do tons of stuff with programs. Okay, and this is, I think, really the basis of why learning actually works. You don't need to model the world. Okay, you just need a good approximator. In particular, another way of saying this is that your model class has to have good coverage. But you really don't care about specificity at all. Okay? You don't care if there's a lot of additional junk there. So suppose, for example, that Greg has a model class. It's really good. Okay? And I have a model class that's pretty horrible. My model class includes everything in Greg's model class, but a lot of junk. Okay? So 1 unit of Greg, like plus 1,000 similarly sized things of complete rubbish and junk. So my model of the world is kind of much worse. Greg has a much, much better sense of the world. He knows much more about the world. Okay? But the thing is, it doesn't help him. Okay? I kind of dominate. Because anything he can approximate, I can also approximate. And my low cardinality is only like what? His low cardinality plus 10? Who cares? That's 10 more samples I need to expand. Okay? So that means that if you have, I dominate Greg. And in particular, whenever you have a situation where one model class contains the other, is more generic than it, and is only like multiplicatively bigger, okay? It dominates it, it's better to use. And that's, I think, the basis of machine learning. Always use very generic hypothesis classes. Don't try to model the world, just have these generic approximators. Okay, and this is like nothing new. Some call it the bitter lesson. Fred Jeleniuk fired his linguists because of this. And this is really all captures the same thing, and I think the core, I don't know why people call it the bitter lesson. To me, it's the happy lesson. Okay, you do not have to model the world. You just have to have a good function, generic function approximator. And now we're seeing it also with transformers. They don't model language in any meaningful way. They're just very, very good generic function approximators. Okay, just a side comment, we talked a bit about the hypothesis classes. Maybe the more correct thing to talk about is description languages, because really the learning rules we use is kind of minimizing some balance between error and length of description. Description language, we can say one description language dominates another. If everything you can describe, in Greg's language, you can describe in my language using just a tiny bit more description, right? So in that case, I'd say my language dominates Greg. And again, it might dominate, it's strictly dominated in the sense there might be things that I can describe that Greg completely cannot. Okay? But anything he can describe, it can also describe system. Okay, so with this view in mind, we can recast this negative result about the pencil that in some sense, standard COT dominates recursive language models. Right? If you want to describe something using this recursive approach, or with standard COT, the cost of describing the standard COT is only a tiny bit more than describing it with pencil. Plus, there's a bunch of things you can describe actually much, much more that are not modular. Okay? And so that means that, again, there's no benefit here. The important thing here is there's no benefit in distribution, because all this analysis was in distribution, was when we train on data sampled from the same distribution we care about. Okay? What about out of distribution? Okay, so this is where things get interesting. The problem is I'm out of time. Okay, I'll still take 3 more minutes. The point is that when this domination result really is only valid in distribution, this domination result also tells us that kind of the exact programming language doesn't matter because they can each simulate each other and exact details of programming language don't matter at all. But actually, if you want to do generalize good out of distribution, they do matter. Let me flash some examples to you. One is in terms of length generalization. You want to write the shortest program. The shortest program will frequently not length generalize. For example, depending on your programming language, the shortest program might contain an array of fixed length because all your examples were less than, 100,000, okay? But of course, the right thing to do would be to write it this way, okay? And now you will work on any length. Now, small details of the programming language that are completely irrelevant for in-distribution, okay, might say that you prefer this way or this way, in which case you will not length generalize or you will length generalize. Okay? Again, in distribution, it's perfectly fine. This approach is perfectly fine in distribution. Because if all your example and training time were less than 100,000, probably most of them in test time in distribution will also be at most 100,000. Okay? Another example is suppose you're solving some classification problem over graphs. Your input is a graph and 2 nodes. In your training data, all your examples are either one of two sorts. You have either 2 separate cycles with S and T, one on one cycle and one on the other, or one big cycle with S and T antipodal to each other. Okay? So now write a program that would classify between these two. Okay? What will your program do? Just think in your head. I'm not going to ask you because I don't have time. But now think about, okay, at test time I have out distribution, and I have something that maybe looks like this. I have 2 with S and T both in here. Okay? Or maybe something that looks like this, one big circle, but S and T here and here. Okay? So the thing is that there are many different ways of classifying between these two. You can just check for connectedness, you can go from S and go to T, you can get a bunch of different things. And which one, they all have almost the same length. In distribution, it doesn't really matter what you use, but out of distribution, it makes a huge difference. Okay? So this dominance is just completely not valid when you're talking about, like, doesn't tell you anything for out of distribution. And in particular, what Chenshao showed for recursive language models in specific is this, I think, very interesting result. It says, as we said before, standard COT dominates recursive language models, right? The description length would never be much longer. Okay, so that means it's kind of always better. But if it's in fact shorter, so you train by minimizing the standard COT, if you actually find a solution that's better than what you can do with recursive language models. Wait, I wrote this wrong, right? Okay. If your solution actually happens to be better than with recursive language models, okay, it's actually worse. Like it might be better in distribution, but you necessarily made a mistake. And what's going on here, I think, is when you think of it as follows. Why would you, if your problem really has this modular structure, in COT, you found this program that uses standard COT that's shorter than the modular program, what you're doing is you're using some shortcut. That's perfectly fine, right? You're actually in some problem, you're not actually solving the sub-problem, you're just saying, oh, I know that in these instances, this problem would have this type of solution, I don't really need to solve it. Okay? You're doing test-taking skills. This is perfectly valid approach in distribution. Shortcuts are great in distribution. But that necessarily means that once I go out of distribution and I encounter the same sub-problem in a different context, I'd be hosed. Okay? So the advantage of I already shifted to the next slide. Okay? So sorry. The advantage. So that means that actually this like dominance advantage of COT when I'm talking about out distribution is actually a disadvantage. And now I'm in trouble. I don't know what to do anymore. Okay? Because I feel like the whole basis of machine learning is this general function approximators. And general function approximators are somehow inherently, they are not good, they are not sufficient for out of distribution. They're not sufficient for learning to reason, which is really what we want to do now. And I don't know what to do. There are several approaches here. Okay? One approach is to rehire all those linguists that we fired in the 80s. And I don't know, maybe we'll do that. I hope this is not the answer because I do still believe in learning. Okay? Another approach is to turn to online learning, and some people are doing that. And online learning does provide some answers here. I still find it very unsatisfying because it tells you kind of like how many mistakes you're going to make, but not when. So we might do them arbitrarily far in the future. We can talk about it some other time. I don't find this the right approach here, although maybe, I don't know. Another approach is to like just analyze everything very case specific. Not talk about things generically, but really emphasize for specific classes, not only specific classes, but also specific in domains and out domains. Okay, this is again extremely unsatisfying. Hopefully, in the next few years, Chenshao will find a different solution. I'm looking forward to reading it in his PhD thesis. But until then, we have to wait because the talk is over. We have time maybe for one quick question. Not really, but anybody has something? Yes.
In the first part of your talk, would it be fair to characterize the goal as inverse reinforcement learning?
Well, I don't know what inverse reinforcement learning means. I don't think there's a definition of that. So I think that okay. So in the reinforcement learning literature, this is referred to as apprenticeship learning. This is the problem that Shapiri actually tackled. When people talk about inverse reinforcement learning, they generally, but again, this is a bit vague, talk about actually learning the reward function, which is something you cannot do. And so this problem of learning to be good based on good demonstrations, exactly kind of our formulation again, maybe with slightly different language.
The class was a class of reward function.
That's true, but I cannot learn it. I am not succeeding in actually learning a reward function. So inverse learning really, usually when people, okay, it depends what you mean by inverse reinforcement learning. In much of literature, what people mean when they say inverse reinforcement learning, they actually mean getting a reward function that has like small squared loss relative to the correct reward function. That's not what we're doing. But this is a semantic difference. I mean, this is like... Okay, yeah, now I'm afraid. Okay. Oh, I forgot to say about the dependence on the context length. Okay, no, that's not what you're gonna. Okay.
No. General question. So, Nati, so as a professor, you train students to like do general reasoning and kind of not in distribution. Can we draw some idea from like how do you train students to train networks, like teaching dimension?
I don't think of teaching them in maybe, but I don't think. Okay, again, the standard definition of teaching dimension I don't think is useful because that. So teaching dimension, maybe okay. So teaching dimension. Okay, I have two different questions. One is teaching dimension relevant. Maybe so. Teaching dimension the way to maybe is relevant because it talks about exact learning, and maybe what you need to move is move from pack learning to exact learning. But exact learning is much harder. I don't know how to do exact learning. Should we gain insight by how we train our students? You know, this is a question I'm grappling with. Like, if you answered me 5 years ago, I would like dismiss you like this. Okay, I really felt like you should think of machines as machines and people as people, and like sometimes it's useful to tell stories about relating them. And I'm not going to dismiss you this way. No. Maybe we should be thinking about that. But the problem is I don't really know. I don't think I can like describe how I train students, and I don't know. I still feel that like history has told us that going to people and trying to like extract from them how they do things or their inductive bias or their like formulate people is like a losing game.
Yeah, this is a losing game, but it's like sometimes useful curiosity if you think about like how do you get this chain of thought
Maybe,
step
yeah. Maybe.
and
Yeah.
decompose.
Maybe. I don't know. I'm waiting for Chin Chow. Okay, thank you.